Welcome back, everyone. Today we get to talk about an old friend. So let's dive in. The statement reads: a charge Q is released from rest at the origin in the presence of a uniform electric field E equal E naught Z and a uniform B field B naught in the x hat direction. Determine the trajectory of the particle by transforming to a system in which E is zero. Finding the path in the system and then transforming back to the original system. Assume that E naught is less than C B naught and compare your results with example 5.2. So it looks like we're going to have some kind of cyclotron motion with the uniform magnetic field. But let's see how it works out and what this assumption means. We'll see that come through. But fun question to tally up. Let's draw it out. All right, so we were told that the E had to point here in the Z direction, B in the X. So the goal is to transform to where E is zero. So this is the idea, is that we're shifting the framework, and this is where the relativistic regime can come in and kind of help us. So let's see how this would work out and what the transformation rules were to be if E is zero in this situation. All right, so with this transformation, the rules for the situation and context is EY sticks with EY because it remains unchanged in the parallel direction. Similarly with BY, but the Z and X components transform, so we just have to tally up what's with and what's against and put in the appropriate substitutions. Again, we've seen these rules before, so I'm not going to spend too much time on it. But for the context, these are the ones we have to abide by. This gives the fields in the system S moving in the y direction at speed v. Now what we see is that E is equal to 0, 0, E naught, and B is equal to B naught, 0, 0. So E bar Y is equal to 0, and E bar Z is equal to gamma E naught minus V B naught, and EX is equal to gamma of 0 plus 0. And that's how moving in the y direction gives us the cancellation of E in that case. So if we want E equals 0, we have to pick the condition here. We have to pick that if we want E naught equals 0, we must pick V so that E naught minus V B naught equals 0. Hence, V moves at E naught over B naught. And the condition of E naught is less than C B naught, if we solve this for the ratio, guarantees that there's no problem getting to such a system. So they give you a little fish hook in the question, and now you see where it comes in. That being said, we could problem shoot this moving in another direction using another set of transformation rules. But here, this is showing you how we can A, set up a system, and B, that is possible. All right, so with B bar Y equals 0 and B bar Z equal gamma times 0 plus V over C squared times 0 equaling 0, we can focus our efforts on B bar Z, which is equal to gamma B naught minus V over C squared E naught. Let that run through. The condition on E naught tells us that we have to be equal to V B naught. So we plug that in and we see that we get a gamma B naught factored out, and then we get 1 minus V squared over C squared. But we see that that is also equal to 1 over gamma squared, so the gammas cancel here, and we like that. So what we end up with in the transform system is a B field that is 1 over gamma B naught x hat. So that's pretty cool. And this is if we have E equals 0 and a constant magnetic field, the trajectory in S bar then, since the particle started at the origin in S, it started out with velocity negative v y hat in S bar, because it has to go the opposite direction. And with the constant magnetic field in S, this should resemble the cyclotron motion. So it moves in a circle of radius r, given by P equal Q B bar r, or if that's the case with the momentum, gamma mv is equal to Q, plug in a B bar, so 1 over gamma B naught r, solve for r. So here we get a gamma squared term in there instead of mv over qb0. So we're looking pretty good there. Just remember with this, we have to add that in if we're moving in one frame without moving in the other. So here we see what the radius of the cyclotron motion is. And let's move forward. Here, if we doodle it out in a barred system, we see that we're going to have to move to the left, put the magnetic field, so we want to do its thing and pull it out in the x direction. So we get the cyclotron motion, radius r, point charge q. Yeah, it's pretty cool in my opinion, but we're not quite done yet. That being said, the actual trajectory is given by, well, it's not moving in the x per se because it's in a circle cyclotron. And here we know that y bar is moving, so it has to be negative r sine omega t bar. Z bar is equal to r times 1 minus cosine omega t bar. That's just how it is in the diagram drawn up to where we see it in terms of Cartesian. And we know that the relationship between omega is v over r from linear velocity to angular velocity. So the Lorentz transformations in this case of relative motion to the y direction read. Now we have the forwards bar or the inverse from bar to the original frame, bar to original, bar to original, bar to original, and the inverse original to bar, or no, I'm going backwards. Either way, you have both sets here. Maneuver accordingly and then solve. This is inverse, this is forward. And then we see that the trajectory in S is given by x equals 0. That's easy because x don't change. And then if we want in the original, we have to use this one. So we see that y bar we can plug in from this formula here. And we see that t bar we have not solved for yet. But we can by using this definition here. So we got to be careful. It's kind of repetitive. That being said, what we see for this is that we have a lot of things going on that we need to take into account. So let's see what we do. We get t-bar in both of these things, so we have to be careful of that particular thing. And you see this is why this gamma term or this parenthesis term here is put in, because we just substituted in this thing here. So now we actually are in terms of everything we need, but you see we are going to start color coding and seeing what we can get as far as cancellations are concerned and how we can deal with them in a forward manner. After we distribute this gamma in, so that's why we don't have a big bracket anymore. But this is going to look this should look kind of familiar. All right, so what we do is we tag that to the other side, so we add it over. That gets 1y over here. And now we see that we could factor that y out, or y gamma out, by this force factor here. And we could cancel a gamma squared term and everything else. What we're going to have is since this is only gamma to the 1, we're going to have to put gamma in the denominator. So we do that. But we see that 1 over gamma squared here is equal to 1 minus v squared c squared, which cancels what this purple term brought over. So we're just left with y on the left-hand side. So that was a way to get rid of one of them. So we like that. That was just a way to isolate, get rid of, and simplify down. But we're still left with a vt minus r over gamma with the sign. And the sign has a y in it as well. So we're going to have to be careful of that. Similarly, for the z inverse, we're going to have to plug in like that accordingly. So we're left here with a y inside the z. Now, in order to isolate the y and z to get them out of the trig functions, we can use the trigonomic term. We can get rid of the trig terms to isolate the y by squaring both of these things and then adding, because we know that sine squared plus sine squared plus cosine squared give us 1. And so that's how we get rid of the implicit definitions here. And let's go ahead and do that. Perfect. So we see what we have here is we're trying to isolate the r sine and the r cosine of one side. And now if we square the left-hand side and the right-hand side accordingly, we get here the negatives drop because it's a square. And if we add them, we see that we get a sine squared of the same argument, adding with the cosine squared of the same argument. After we factor out at r squared, gives us r squared times 1, so we're good. But now adding them together shows us that we have a gamma squared times a y minus vt squared plus r minus, or excuse me, a z minus r squared. Well, absent of the gamma term that we're going to have from transforming it, this would look like a cycloid that we found back in chapter 5. The gamma squared term makes it, as it were, an elliptic cycloid, as pictured in figure 5.7, but with the horizontal axis stretched out. So this is a remarkable fact that we saw earlier. And here you go, it's just rolling, 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 except it would be stretched out. That is so cool that we have the same result in the classical frame from a relativistic perspective, with, of course, the additions of the relativistic regime. But that being said, the fact that this thing is so consistent with everything makes this theory so wonderful. It also gives us another lens to help us because our toolbox could always use expanding. But that being said, this gives us a way to verify also if we're ever curious about how something's moving. Because of the particle moving to the left in the transform frame versus starting from the right and letting the fields do the work. So now that we're verified there, I think we're ready to move on. So I'll see you at the next one.